Welcome to the very first episode of NASA Science Live. This is our chance to take you behind the scenes so that you can get to know your space agency. I'm your host, Sophia Roberts, and today we're going to talk about the moon. But before we get into that, here's some of NASA's most recent news. We were all broken heart emojied to say goodbye to the Opportunity rover. But this really was the little rover that could, because it lasted 15 years, despite the original mission proposing for it to last for 90 days. We lost contact after a planet-wide dust storm. But, you know, it's not all sad, because this really afforded us a whole new generation of Mars exploration. Hashtag thanks, Oppie. Well, when this mission ended, we were proud to announce the beginning of a new mission, and it's going to look at the origins of the universe. This is called SphereX, and it's a look at one of the biggest mysteries in science, namely, why did the universe expand so rapidly, like under a nanosecond after the Big Bang? I know. Well, let's zip forward a few billion years, and NASA is expanding the way that we do science. Instead of designing and building and sending out lunar rovers, we are going to buy space on landers from commercial companies. This will hopefully fast-track some of our science, so much so that we may have new science on the moon in as early as the end of this year. So, speaking of the moon, let's talk about our cosmic next-door neighbor. It's been 50 years since we first went to the moon, and the moon remains one of humanity's greatest achievements. So today, we're going to talk about what it takes to go back. It also generated a lot of brand new questions. So, because as science always does, we need to go back to find out more. Over the course of our show today, we're going to talk about a few important things. Obviously, our Earth's moon, the lunar legacy, we're going to talk about lava tubes, some moon mysteries, and our Ask NASA portion. And this is the most important part because this is a chance for you to ask us questions and for our experts to answer them. So our new goal is to go back to the moon for long-term exploration. And this has a whole new host of challenges that did not exist 50 years ago. Why are we going back to the moon? Because it really is the key to both the history of our Earth, our solar system, deep space missions to Mars. But with all these new challenges, we have to understand its environment. Just to give you a frame of reference, the longest any Apollo astronaut was out there was just over 3 days. And to go back long term, we need to understand its environment. One huge and critical thing we have to think about is the radiation. Now here on Earth, we have the atmosphere, which is going to protect us. But out on the moon, anything we send out on the moon is going to be baldly exposed. So let's hear a little bit more about that.
To every astronaut or spacecraft, the sun is a damaging source of radiation. All objects traveling through space must contend with this hazard, including planets. Even the moon has the scars to prove it. New NASA research suggests that some of the coloration we see on the moon could actually be a form of sunburn.
The leading hypothesis is that the magnetic fields are blocking some portion of the solar wind from reaching the surface.
The solar wind is the sun's continuous outflow of particles and radiation that fills the inner solar system. Earth's magnetic field provides a strong global shield against it. However, the magnetic field on the moon is much weaker, and it forms only small, localized bubbles of protection. In these spots, the sun's particles can be reflected back into the solar wind or funneled to nearby regions. The shielded areas under the magnetic field form pale swirls. Those bordering parts become darker. The contrast is so prominent, we can actually see it from Earth.
The magnetic fields in some region are locally acting as this magnetic sunscreen. You know, sometimes you put on sunscreen and you miss like a tiny little bit, and then you have a really bright red spot on your skin where you missed it. That's in some ways the analogy of this sort of region of the moon that is extra exposed.
Unfortunately, the moon's patches of magnetic field are not robust enough to completely protect human explorers from the sun's radiation. But further study of lunar magnetic fields could lay the groundwork for future innovations.
Well, what if we got a strong enough magnetic field that perhaps we could produce artificially? That's a question that I think remains to be answered, but the crustal magnetic fields on the moon and lunar swirls kind of provide a hint in that direction that we might be able to learn something about.
So with us today, we have 3 experts that are going to give us a better idea of what it's really going to take to go back to the moon. We have Dana Hurley, who's a planetary scientist, Noah Petro, who is a project scientist with the Lunar Reconnaissance Orbiter, and we have Kelsey Young, a research space scientist. All right, Dana, since you're right here with me, I'm going to ask you the first question, which is, what really do we need to consider to have what they're calling sustainable presence on the moon? And really, what does that in lunar environment look like?
Okay, well, so a sustainable presence on the moon means that we have astronauts that are going to be there for a long period of time, or we have astronauts that are coming and going, and being able to go out to do experiments across the surface and that sort of thing. So we need to protect them from that radiation that the sun is spitting out and that's coming through the solar system from the galaxy. And so one of the ways that you can do that is by building shelters for them. So if there is some eruption of particles from the sun that's sending out a burst of high energy particles, they can get out of the way. But yeah, so that's the big environment that we have to deal with for our astronauts.
And have I also heard something about there's a bit of water also on the moon?
Yeah, that's really enabling if we want to have a sustainable presence on the moon, is that there is water in these permanently shadowed regions near the lunar poles. And if we can use water that's already on the moon, then that means that we don't have to take it with us. And that's a big cost savings, and that will enable us to send more missions to the moon. If we don't have to take everything with us, we can use products that are right there.
And just really quickly, like, how much water are we talking about here? Is there a lot, or is it?
Well, so it's a lot for the moon, because about 10 years ago, we didn't think that there was any water on the moon. And just over the last 10 years, we've discovered that there is this water here. And we probably could fill up maybe 1,000th of Lake Erie if you put all the water that's distributed through all those permanently shadowed regions together. So there's some water.
All right, Noah, I want to lob this next question to you, because you've had the opportunity to study it a little closer than we are here on Earth, studying the Lunar Reconnaissance Orbiter. So what do we know right now about the lunar environment today, and then what are we looking at today? So what have we, I guess, learned over the course?
Yeah, I mean, we have the benefit with the moon of having had 50 years of understanding, starting with really even the precursor to Apollo, but specifically with Apollo, humans on the surface of the moon, the experiments that we left behind on the moon to understand what's happening there. Measuring the radiation environment that Dana talked about, measuring the solar wind that's coming and planting itself into the lunar surface, but also understanding the changes that are occurring on the moon, how many moonquakes are occurring, the dynamic environment at the moon. So for 50 years, we've had the Apollo data, but for the last 10 years, we've had data from the Lunar Reconnaissance Orbiter. And what that data is showing us is really how the moon is changing. We've been able to observe new impact craters that are forming just about every day. It's changing the surface gradually. We're able to detect new environments at the moon. Dana talked about the poles of the moon, and these are really unique environments, some of which receive no sunlight, coldest temperatures in the solar system measured in these permanently shadowed craters. And so the combined data of Apollo and LRO is telling us that there's these really unique environments at the moon, some of which may provide shelter for future astronauts. We're seeing lava tubes that may exist beneath the surface of the moon. And so we now have this really robust picture of the lunar environment, its dynamics, how it changes. And boy, do we have a lot of places we'd love to go. We've identified a huge suite of places on the surface that would compel us to explore further on the moon.
I mean, you've talked about these impact craters. Is that something that really is happening daily, monthly, yearly? Like, how exposed would things be to it?
Yeah, I mean, there's this constant bombardment of micrometeorites on the lunar surface. The moon's being sandblasted all the time. Apollo astronauts were on the moon, as you said before, for as short as a few days. If we want to be there longer, we need to know how the moon's changing and what threat that poses to future astronauts.
All right, so you're lucky to have something close to the moon, but we don't always have that opportunity to. So Kelsey, I know you study things about other planets here on Earth. Can you tell us a little bit more about how we do that?
Yeah, absolutely. So we've heard a lot about Apollo. The Apollo astronauts were able to collect an amazing suite of samples that we're using right now today to learn new things about the moon. A lot of the water discoveries that Dana mentioned were found actually from studying moon rocks that were collected 50 years ago. But technology's come a long way since Apollo. We've been developing handheld instruments that astronauts would be able to use in their gloved hand to understand the geochemistry and the mineralogy real time of rock samples on the moon. We're developing geophysical techniques that we need to understand now by going out and testing these things in terrestrial analog environments here on Earth to be able to understand how exactly astronauts in the future will be able to use these instruments. We also want to go out to terrestrial analog sites to study scientific processes. What processes here on Earth do we actually see forming on the lunar surface as well? And one of those things is, just as one example of many, is lava tubes. We see lava tubes here on Earth that are incredibly exciting. We also think we see evidence of them in the Lunar Reconnaissance Orbiter data of seeing these features on the lunar surface as well. It's really exciting.
Yeah. So this is our chance now to have you guys have your questions answered. So if you go to Twitter and use the hashtag AskNASA, or in the comments below, you can send your questions along. So far we have one from Mark, who asks, do we have good materials to block the solar radiation, or is it something that still needs to be developed?
Oh, that's a great question, Mark. So actually, the soil that is on the surface of the moon is really good at blocking the sun's radiation. From the Apollo samples, we see pieces of the solar wind that get lodged into the smallest grains, and they're stuck just on the very, very surface. So you don't need a whole lot. So we can use that soil, to build walls or to, provide shelter.
Great. We have another question here from Facebook, and it is, if the moon has no atmosphere, how can there be water?
That's a very good question. And in fact, the moon does have a little bit of an atmosphere, but the atmosphere of the moon is so small that when the Apollo capsule landed and opened up the door and let out the air that was inside, it doubled the entire moon's atmosphere. So, but it's very interesting. The moon gets hit by comets, and those comets have water in them, and if that water lands where it's really cold, it actually freezes into ice, and can be stable. It's so cold that it won't evaporate in billions of years.
But we're not talking about flowing water, rivers, oceans. This is a single layer of water molecules, maybe chunks of ice beneath the surface. So when we talk about water, we're not talking about water that we see after a rainy day here in Washington, D.C., or, at beaches. We're talking about this very different environment. The driest desert on the Earth is far wetter than the moon. So let's make sure we have a good picture of what's actually there.
I mean, how would we get that then? Like, how would you collect enough to do anything?
Well, that's a great question. I mean, so you have to heat it up, basically, because the water is stuck to the surfaces, and if it's warmed up enough, it will leave. And the reason why it sticks is because it doesn't quite get warm enough. So you can go through and you can gather up a lot of the soil that has the water stuck to the surface and then heat it up and collect it.
Yeah, and that's one of the ways we know that the moon is so different than the Earth is, you look at any moon rock. Even the wettest moon rocks we have such a small amount of water that for 40 years people thought there was no water on the moon. Well, it's just a small enough amount that we actually couldn't measure it properly until the instruments got advanced enough to be able to tell us that it's there.
Right.
All right, so Janice from Twitter is also asking, considering the future of lunar exploration, what do you think the current debate is about the past? Should the landing sites of the Apollo 11 be protected as a cultural heritage site?
Yeah, absolutely. I mean, these are some of the most important sites, both for our nation's history and for the history of humankind. So I would absolutely argue that these are incredibly important sites we need to preserve. We all are also still learning a lot of things about the rocks collected at these sites. So I think there's still a lot to be learned from these sites, but absolutely their preservation should definitely be on our minds.
Yeah. I also think that it'd be valuable to go back to maybe one of the landing sites to see how the material that was left behind has changed. There we have equipment that's been on the surface for 50 years. How has it been worn by being exposed to that radiation environment, by micrometeorite bombardment? So there's a science question to be asked at one of the 6 Apollo sites as well. But maybe we keep Apollo 11 and 17, keep those pristine.
Yeah.
All right,
And absolutely, by studying that too, I think you can learn a lot about a sustainable presence on the lunar surface when you understand how the environment is reacting with the technology that you bring to the lunar surface.
All right, we have one more question that we can ask for this segment, which is from Peggy on Twitter. What would be the most important tool that we could use on the moon to tell us about its inhabitability?
Well, I think measuring the radiation environment on the surface.
That's right. Yeah, that would definitely be helpful. And also to quantify what resources are there that we don't have to take with us. So finding out where that water is. So being able to understand whether that water is only in the polar regions, how much of it is at lower latitudes.
All right, thank you all for your questions. We are going to be answering more questions later on in the segment. But we really need to talk about these lava tubes that Kelsey had mentioned earlier today because that is so exciting. So let's take a look about what those are all about.
The moon originally was a big ball of magma. Through time, as the crust formed on the surface, the magma on the interior also slowly leaked to the surface. A lava tube is essentially a cave, an enclosed tunnel through which lava flowed, and if it was able to drain out, you now have this open cave through which you can conduct some interesting scientific experiments. Here on Earth, a research team studies lava tubes as a means for better understanding how we can explore and understand lava tubes on other planets and the moon. From some of our high-resolution images from the Lunar Reconnaissance Orbiter, we can actually see pits on the surface of the moon, and it looks like these could be the extensive lava tube networks. So they could be pathways that are tens to hundreds of meters long, they could be kilometers long. Understanding lava tubes, where and when they formed on the surface of the moon is just a really exciting scenario. These caverns have been protected from the space environment. So this really would be an ideal place to try and collect samples that tell us not only about the moon, but about the solar system in general and how it's evolved through time. Our next step's starting to plan robotic exploration of the moon again, and this might involve observations that would help confirm the presence of lava tubes or some of these subsurface void spaces. They may even be accessible by robots or in the future maybe even humans. To me, it just makes them a very interesting and exciting aspect to studying the surface of the moon.
Oh, that is so cool. I mean, there's really just a whole new world underneath the surface of the moon that we just still really need to explore. So, Kelsey, I know you know all about this, and that was just a taste of these things. So can you tell us more about these exciting lava tubes, and what else do we need to know that's out there on the moon to explore?
Absolutely. So terrestrially, when we look at lava tubes here on Earth, they tell us a lot about how the lava flows that you find them in were in place. So it tells you something about the volcanic history of that terrain that you're working in. We think the same thing about lunar tubes. By exploring terrestrial tubes here on Earth, we're able to learn something about how the terrains where we see the lava pits and potentially lava tubes on the moon formed. So we go out to these lava tubes here on Earth. We use handheld portable instruments that astronauts can use when they're on the moon to traverse on top of the tubes to actually image what's underneath the surface without actually having to go anywhere near the pit itself. So by doing this fieldwork here on Earth with instruments above the ground, you're actually able to understand what's below and actually perhaps deduce the volcanic history of the lunar surface.
Really wonderful. Let's answer some more questions, all right? Using Twitter, #AskNASA, or in the comments below. And if you're just tuning in, this is NASA Science Live. So Janice on Twitter, well, no, we already did this one. Krish, I'm sorry, on Twitter is asking, what bachelor qualifications are there required for an internship if you wanted to join NASA?
Yeah, I would definitely say that NASA takes all kinds. I think science, technology, engineering, math, I mean, those are certainly normal paths forward to get into NASA, but we're really interested in all backgrounds, art, business, communications, media. NASA really needs all types to make our mission happen, and I would really just say follow what you're passionate about, and that's the best way to get involved, in my opinion.
Yeah, I think NASA attracts people who are just interested in learning more, and like you said, whether it's the science engineer or humanities, you know, NASA has a history office. The people who are putting on this show here are all NASA employees, and so NASA has this rich family from diverse backgrounds that really kind of make NASA such a unique and special place to work. But we also get great people coming from outside of NASA who we get to work with as well.
Yeah, so I work at Johns Hopkins Applied Physics Lab, which is just up the street here in Maryland, and we have interns working there as well. And we have interns that have, you know, math and computers and science and engineering backgrounds, and we also have all sorts of other work that we do.
All right, let's get back to the science. Jeremy on Facebook is asking, would those tubes under the moon possibly contain oxygen?
On the moon, probably not, but they actually could contain usable resources. There's a tube that we work in out in California that has ice buried way deep below the surface in an otherwise very hot desert environment. So it's possible that tubes contain something that eventually down the line could be used as a resource once we figure out exactly what's down there.
All right, we have a class asking us, and it's an earth science literature class on Twitter asking, from a 6th grade class, which is great. If you could jump high enough on the moon, could you fly into space?
Well, it's not just about jumping high, but also fast. The moon's got weaker gravity. It's 1/6 the gravity here on Earth, and so we've all seen the videos of the Apollo astronauts leaping around. Well, I suppose if Jack Schmitt had had his Wheaties that morning and jumped really high, he could have gotten enough speed to get up to go, leave the surface of the moon. But I'm not sure even Jack with Wheaties would have been able to jump, 1.5 kilometers per second, 2.5 kilometers? 2.3 kilometers per second to actually leave the gravitational field of the moon. Just jumping far enough is pretty cool. Looks, it's kangaroo hopping around the moon seems like a pretty good way to spend an afternoon.
But when you all 6th graders grow up and if you can make it to the moons of Mars, you could hop off of those. But don't do that because you want to be able to get back down.
Yeah.
It'd be pretty awful just to be floating out there without any other help. All right, CJ on Twitter is asking, are there any new moon missions being planned or constructed anytime soon?
Well, you mentioned earlier today, we've got this commercial program that's coming up with launches perhaps as early as this year. And so there are going to be missions going to the moon very soon. Just last week, SpaceX launched an Israeli mission to the lunar surface. And so I think we're at the precipice of this new generation, this new era of lunar exploration with frequent smaller missions that can bring scientific payloads to the surface. And we'll usher in this new era of asking these focused questions on the lunar surface. I mean, we all anticipate a time when there may be bigger missions, and NASA has a process for proposing to do that. So that's in the pipeline. I guess I'd just say stay tuned because it's going to get very busy at the moon. We hope to get some company joining LRO and Artemis at the moon very soon.
All right, we have time for one quick more question, and that's for Manish on Facebook. Is one of the uses of mining water on the moon to provide fuel to propel us to Mars? Oh.
That's a great question, and yes, that is something that we can do because even though the moon does have a gravity well, as we just discussed, it is less of a gravity well than the Earth's gravity well, so it's less expensive to launch propellant off of the moon than it is to launch it off of Earth. So if we want to send anything, robotic or human space missions to Mars, then we could use fuel that we get from the moon, that we make from water there.
All right, thank you for submitting your questions. I want to send you guys some of my other questions really quickly. So the one final big question really for each of you, because NASA is gearing up to send all these new things out to the moon. So what are each of you guys looking forward to researching out there? Like, what moon mysteries do you need to know?
I would love to send something to one of those magnetic field regions on the moon that was in the earlier segment and understand how well those block the solar wind and what happens when you're close by there, and you can look to see how that solar wind is interacting with the surface of the moon and if it's even making water.
For me, I think the moon has this great intersection of both planetary science, earth science, heliophysics. So what would interest me is going to a location on the moon and drilling. The deeper you go into the lunar surface, the busted up soil, you'd be able to go back in time. And so if you drill deep enough, you might expose a layer that was at the surface of the moon 4 billion years ago. And by measuring that, understanding that, we'd understand what was happening on the sun 4 billion years ago and understand how different that time was than it is today.
For me, I think going back a couple decades ago, we thought that the moon was a fairly, it had been dead for quite some time. There really hadn't been a lot going on, but we're finding more and more that it's a very dynamic and, relatively speaking, young planet. We see evidence of volcanism from only a couple decades of millions of years ago. We're seeing active micrometeorite impacts on the surface. So I think understanding the recent past of the lunar history, which is never something we thought about being able to do, is something I think is really important.
Excellent. All right, we actually have time for one other question, which is great because we talked a little bit about at one point our diverse backgrounds coming either through internships, and I'm wondering how you guys did make your way to NASA.
So I studied physics in college, and then I went to grad school and got a PhD in the field called space physics. That's understanding that space environment and the sun and that sort of stuff. And then I had an internship at NASA, or a postdoc at NASA, that started my career.
Yeah, for me, I had great teachers who pushed me, encouraged me. My father worked on Apollo, so I was always just interested in space. But I had high school teachers who said, geology is great. And so I became a passionate geologist, unraveling the history of the Earth. And then I had a college professor say, you know, you can do geology of planets. I thought, oh, that sounds pretty cool. I'll do that. And so I did a summer internship at the U.S. Geologic Survey in Flagstaff, Arizona, which is a beautiful place to be. And that opened my eyes to the world of planetary science and what this career means. And then just sort of on this path of going to grad school and eventually ending up here at Goddard. It's a great path, but all because of encouragement of both family and some amazing mentors.
Yeah, and for me, really quickly, similar story to Noah's actually. I found field geology in undergrad, so the ability to be able to go out in the field for work and solve puzzles, essentially is what we're doing, was just completely fascinating to me. So when I was looking for graduate schools, I thought to myself, you know, being able to do this on other planets, are you kidding me? This is a job. So I actually, same thing, I got my PhD funded in part through NASA, came here for a postdoc, and I'm still here years later, so never left.
In just like 5 words or less, if you could take one thing to the moon with you, what would you take? If you could go.
Oh gosh, I would take a camera and do selfies all over the place.
I'd take a rock hammer and get as many samples as I could to bring back and study here on Earth.
5 words or less, I guess. In situ analytical technology.
You have one more word left.
Exclamation.
Yeah.
Well, we have actually one last thing from Patrick on Twitter, who's asking, could we ever raise animals or grow food there on the moon?
Yeah, I think we'd have to do it in an enclosed environment, in a habitat. The space environment's not suitable for life, so anything exposed to the surface would not thrive. But if you had a large enough enclosed space, the lunar module on Apollo sustained 2 astronauts for multiple days. Make that bigger. Bring your dog, bring your cat. I don't know, you could have a little farm there, but you need the space to do it. And growing in there would be fun. There are experiments on the space station where they're trying to grow vegetables. I mean, the idea of sustainability. We can't bring all the food with us. We're going to have to grow some of it. Everybody remembers growing potatoes on Mars. I don't think we could use lunar soil to grow potatoes. I don't know if there's enough nutrients in it.
I don't think so.
But if you bring your own soil, bring your own fertilizer, make your own fertilizer, you might be able to do that in your habitat.
All right, wonderful. Well, thank you guys for participating with this, and I want to thank all of you for also participating and sending in your questions through the Ask NASA hashtag. We will also be able to answer more questions. Our scientists are going to stick around a little bit to do it via the internet. We chose to do this live, you guys, because we really want to fuel your curiosity, and we think that answering questions helps all of us understand the universe. So if you have more questions, keep sending them along. And to learn more, go to go.nasa.gov/NASA Science Live. Next time, we're going to talk about what it takes to go interstellar. So see you all next time. Hello and welcome to NASA Science Live, an opportunity for you to come behind the scenes and to get to know your space agency. I'm your host, Sophia Roberts. This show is really all about you being able to interact with NASA scientists and to get your questions answered. So please visit us on Facebook or Twitter and ask us a question using the hashtag AskNASA, or leave a question in the comment box wherever you're watching this. Let's get started with some of the latest news from around the galaxy. Scientists were surprised to learn that near-Earth asteroid Bennu is not only more rugged than expected, but it's actually erupting plumes of particles from its surface. Two facts that are sure to give spacecraft navigators a little asteroid indigestion. But never fear, NASA is up to the task of collecting a sample from this asteroid and sending it back to Earth. In other news, the agency rolled out its Moon to Mars program that will see astronauts living and working not only around the moon, but on it. Before you know it, we'll all be like Matt Damon, making space potatoes. But maybe let's bring our own fertilizer. All right, moving on to matters of international appeal. NASA signed on an agreement with the Brazilian Space Agency on an upcoming mission in the form of a teeny-weeny satellite. It's called a CubeSat. This small spacecraft, cutely named Sport, is about the size of 2 loaves of bread and will investigate 2 phenomena that happen above our planet that disrupt radio communication systems, satellite technologies, and even GPS signals. I don't know about you guys, but I need me some GPS. I honestly wouldn't have even been able to find the studio without it. So, go Brazil! All right, that is all the news we have for now. Today's episode is all about interstellar space, and the topics we'll cover will take you to the edge of our solar system and beyond. We'll show you how big our galaxy is, check in on the Voyager spacecraft, and explore the region beyond our bubble. And you'll meet a really special student that is helping us hunt down planets that orbit other stars. So just to give you guys some basics, interstellar space begins where the sun's flow of charged particles ends. And we call this bubble of particles the solar wind. It extends well beyond Pluto's orbit, but not all the way to the edge of our solar system. Our solar system actually continues all the way out to the Oort cloud, where billions of comets still cling to the sun's gravitational pull. But remember, when we enter interstellar space, and even when we leave our solar system, we're still within the Milky Way galaxy. So, just how much do you think you know about our cosmic neighborhood? Let's find out. Join me and 2 astrophysicists as we play That's a Big Galaxy! All right, our first contestant is an astrophysicist and football lover, Dr. Nicole Colon. And our second contestant is an astrophysicist and sci-fi nerd, Dr. Aki Roberge. Thank you both for joining me.
Thank
you. This is how all of this is going to work. If you get our questions right, yeah, but if you get them wrong, so no pressure here.
Okay.
Great. All right, question number 1. If the Earth was the size of a basketball, the sun would be A, 20 feet in diameter, B, 1,000 feet in diameter, or C, 100 feet in diameter.
Okay.
So basketballs like this.
So that's about that big.
Yeah.
Okay, so Earth across the sun. So you can put, as I recall, about 100 Earths across the sun. So
Okay, I'll take your word for it.
call that a
Sounds right.
call it a foot. So 100 feet. Was that one of the choices?
Yes.
Okay. That was easy.
It is 100 feet in diameter. I mean, the sun, we really know, is huge, but how big is it really? And to be more precise, since we do have some scientists with us, it would be about 109 Earths that fit across the diameter. And it would actually take 1.3 million Earths to fill the sun's volume.
That's a lot of Earth.
That's a lot of Earths. All right, let's move on to question number 2. If the sun and the Earth were separated by 5 pieces of toilet paper, how many would separate the sun and the boundary of where Voyager 1 crossed into interstellar space? Would we have 18 sheets of toilet paper, 203 sheets of toilet paper, or 602 sheets of toilet paper?
Okay. So toilet paper,
yay big, yay long. Well, actually, all right.
Doesn't matter, right?
No, it doesn't
Actually,
matter
yeah.
because we know the distance from the Earth to the Sun is what we call 5 pieces of toilet paper, and that's like 1 astronomical unit, which is literally what we define as the distance from the Earth to the Sun on average. And Voyager is about 100 astronomical units outside, away from the Sun. So if you just do conversion, 5 times 100 is about 500, and I think that was close to one of your answers.
Yes.
Okay.
It really is 602 sheets of toilet paper.
Close enough.
And just to give you guys a little more context, using this analogy, Mars would clock in at 7.6 pieces of toilet paper. Jupiter would all the way be at 25.9 pieces, and then you would need a whole nother roll to get to Pluto at 196.2 pieces of toilet paper.
That's a lot of toilet paper.
It really is. But I hope this helped you guys all understand really sort of how large our galaxy is.
That's right. And that's just our solar system, right? So even the closest star is much further away from that.
Yeah. Though, but actually I wanted to kind of make one point though here though. So for the viewing audience, I'm a professional astrophysicist, and I would normally solve questions like this exactly the same way you would. I would type them into Google. Okay. So for me, the most important part of my job is actually more about coming up with those questions that actually, the right questions to actually push the boundaries of knowledge into the unknown. And that's the actually really exciting part and the fun part too. So, sorry.
All right, I want to thank you both for participating in our game show.
Thank you.
Thank you so much for playing That's a Big Galaxy. And our astrophysicists will be returning later on. So please send us your questions using the hashtag #AskNASA. All right, so as you just heard, our solar system really is huge. In fact, the Voyager 1 and 2 spacecraft, both which launched in 1977, needed to travel for 35 and 41 years respectively before they even left the boundary of our sun's influence. I mean, at their current speed, it would actually take the Voyagers another 75,000 years to reach the next nearest star system, which is Alpha Centauri. So the fact that 2 spacecraft, which were built in the 1970s and located more than 11 billion miles from Earth, are still working and communicating regularly is simply mind-blowing, for me at least. So in a moment, we're going to be joined by an expert from the Voyager mission, live from Mission Control at NASA's Jet Propulsion Laboratory in California, which they refer to as the center of the universe. But first, let's take a look at some of the amazing milestones of the Voyager 1 and 2 spacecraft.
3, 2, 1. We have ignition and we have liftoff. We have liftoff of the Titan Centaur carrying the first of 2 Voyager spacecraft to extend man's senses farther into the solar system than ever before.
They were launched in 1977. That's really 2 generations ago. You can think of what the technology was. Your smartphone has 200,000 times more memory than what the Voyager spacecraft have.
Voyager 2 was the one that was chosen to do the grand tour, that is to fly by Jupiter, and then Saturn, and then Uranus, and then Neptune. Voyager changed our view of the solar system, really.
Every planet we flew by, we got more questions than answers. They whet our appetites for more.
We were on a path we hoped to get to reach interstellar space while we still had power on the spacecraft to transmit the data back.
The team has been looking forward for this for a long time and really working hard in an engineering sense to make this happen. It's exciting that we've been able to get it into interstellar space and to keep all the instruments on.
A real opportunity on Voyager 2 is because we have a working solar wind instrument to measure interstellar wind for the first time directly. The wonderful thing about the journey is it's still discovering new things because it's going where nothing has been before. And they will continue that journey for billions of years, orbiting the center of the Milky Way galaxy.
All right, I'm really excited because we are joined by a Voyager expert, Dr. Suzanne Dodd, who's calling in from NASA's Jet Propulsion Laboratory in California. Hello, I'm really excited to be talking to you, so thanks for joining us.
Thank you for having me on.
Yeah, so can you please tell us where you are right now? Because I can see behind us that this looks really cool. So can we just start off with saying where you are?
Yeah, sure. The room that I'm sitting in is called the Mission Control Center. It's here at the Jet Propulsion Laboratory. And what happens in this room is it's where we control the very large antennas on the ground that we communicate with the deep space missions, so that all the data that comes back from NASA's spacecraft that are out in the planets or beyond, such as Voyager, that data comes down through these deep space network antennas and into this room. So we really are the center of the universe.
And can you tell us where the two Voyagers are right now?
Sure. Voyager 1 is up and out of the plane of the planets. It went by Jupiter and then Saturn, and it went up and out of the plane of the planets, whereas Voyager 2 went by Jupiter, Saturn, Uranus, and Neptune, and down and out of the plane of the planets. So Voyager 1 is approximately 13.5 billion miles from us here on Earth, and Voyager 2 is approximately 11 billion miles from us here on Earth.
And are we communicating with them right now or soon?
We certainly are, yes. For the Voyager 2 spacecraft is communicating with our deep space network that's located in Canberra, Australia. It's using the large 70-meter antenna dish.
And how do you know that we're communicating with them right now? Is there a way to see that?
Well, yes, you can see it. Actually, any of the viewers can see it on a website called DSN Now, but it's on the screen right here. You can see in the lower left-hand corner there's a VGR2 that's tracking under DSS 43, which is the large antenna in Australia.
So I'm sure that all of you out there right now are curious about the Voyager space mission. So I'm just going to turn it over to you guys in the public so you can ask our doctor some questions. So I'm hearing that Bruno from Twitter is asking, what kind of data are we expecting to gather from the Voyager interstellar mission?
Good question. Voyager is really like a weather satellite traveling through interstellar space, and what interstellar space is contained of, it's dust from other stars. So what Voyager is measuring is the density of the dust and plasma that it's traveling through, the directions that these dust particles are coming from, and also it's measuring the magnetic field that Voyager is traveling through.
All right, amazing. All right, and Carlos on Twitter is asking, is the speed of Voyager 1 and 2 changing in any way? And if so, why? And what are the implications if they are?
Well, actually, the speed of Voyager 1 and Voyager 2 is constant. They're approximately going 35,000 miles per hour. Voyager 1 is a little faster and Voyager 2 is a little slower, but their speed was set by the last planet that they left. So after Voyager 1 left Saturn, its speed has been constant since then. Similarly, after Voyager 2 left and flew by Neptune, its speed has been constant since then.
All right, Mapatag on Twitter is asking, has there been any wear and tear on the Voyagers as they've traveled through space?
Lots of wear and tear. These spacecraft are over 40 years old, so things have broken. And we have to work around that as engineers. We have to figure out clever ways. We can't go to the spacecraft to fix them, so we figure out clever ways to work around what no longer works on the spacecraft. And it's truly remarkable that we've kept these spacecraft going for over 40 years.
All right, thank you, Suzanne, so much. That's all the time we have right now for the Ask NASA. So, but we will be returning to that later on. So let's get back to some of our science. Please keep sending your questions our way, though, because we will be answering some later. But I do want to just recap on some of the incredible numbers that we've talked about so far, because, I mean, it's just amazing that it's going to take another 75,000 years for Voyager 1 to fly anywhere near another star. And the planets outside our solar system, even in our cosmic neighborhood, are just really, really far away. So it's actually remarkable that spacecraft can even study them. Which brings me to TESS, NASA's Transiting Exoplanet Survey Satellite. And it scans the sky looking for planets that orbit other stars. But let's take a minute to understand exactly where TESS is looking.
For the longest time, space seemed like a big, nearly empty place. And we were really only familiar with
our home, Earth. But as we learn more, we realize there was actually a lot out there, including planets orbiting the Sun and even other stars. Enter Kepler, a space telescope that radically changed our understanding of planets outside of our solar system, also known as exoplanets. In finding thousands of new planets, Kepler showed that there are more planets in our galaxy than there are stars. But Kepler looked at only a small fraction of the sky, and many of the planets it discovered are too far away to study in much further detail. And that brings us to TESS, our newest planet hunter. The Transiting Exoplanet Survey satellite works like Kepler, and over the next 2 years, it will scan almost the entire sky. By looking at closer and brighter stars, TESS will find and measure the sizes of dozens of small nearby planets, best suited for detailed investigation by powerful telescopes on the ground and in space, like the future James Webb Space Telescope. And by doing that, we might finally begin to answer the question of whether Earth is alone, or whether there are worlds out there like our own, small and rocky, covered in oceans and dense clouds, or even, possibly, capable of supporting life.
TESS project scientist Dr. Patty Boyd. Thank you for joining us, Patty.
Thanks for having me.
And as we just learned a little bit about TESS, but I want to just ask you, where is it looking?
So it's really exciting to be talking about TESS when we're celebrating Voyager, because as the Voyager spacecraft kept going out and further away from Earth, TESS is very different. TESS is orbiting the Earth. So we come back very close to the Earth every 2 weeks, and we return our data to the ground. And what we're doing is we're looking at our nearest neighbor stars, so the brighter stars in the sky, which are typically the closer stars. We are looking at those stars, searching for planets around them. So those are called exoplanets. And when Voyager was launched, the only planets we knew about in the entire universe were the ones in our own solar system. But TESS, one of our newest spacecraft, launched less than a year ago. Now we know there are planets everywhere in our galaxy, and TESS is taking that next step to find planets around our nearest neighbor stars.
So we're still talking about things inside of the Milky Way galaxy at this point?
Very much so. Really just taking those first few steps from where we are in the Milky Way.
So still very much in our cosmic neighborhood, right?
Perfect, yes.
Yeah. Which is amazing that we can still find so much so close to us. And then there's so much further away even to consider later on.
Right.
Yeah. So how does TESS look for and find other planets? Like what process is
So it uses the same method that Kepler used. It's something we call the transit method. And Kepler gave us a great answer about the Milky Way. It told us that planets are everywhere, and there are more planets in the Milky Way than stars. So that means the TESS can take the next step and determine where are the closest stars. And the way both missions do this is they monitor the light from many, many thousands or millions of stars all at once, and they're measuring how bright the light is, and they're looking for a very tiny dip in the light called a transit that happens if the system is perfectly aligned between the observer and the sun, the star. You see a tiny little dip in the light from that star. That's called a transit. The planet goes around, you don't see anything, and the next time it comes around, you see another little transit, and that tells you the orbit of the planet. And if you know the orbit of the planet, you can tell how far away it is from the star.
Just a little blink in that light, right?
It's a very tiny blink. You have to have a very precise ability to measure the light, because we're talking about hundreds of parts per million. And actually, the smaller the planet, the smaller the dip. So we actually get some information about the size of the planet just by measuring the dip or the transit.
And so, of course, everyone's always wondering about potential life. So are we looking just within the habitable zones or other ones, or where precisely are we, concentrating our efforts?
So TESS is basically searching for transits of anywhere between less than a day length. So those will be planets that are really zipping around their star, very, very close to the star. They're lava worlds. All the way out to planets that would orbit on, say, month-long timescales. So around small stars, that would be far enough away that they might be in what we call the habitable zone. And that's a very special area near a star where the planet isn't too hot that all the atmosphere would be vaporized or blown off even, and it isn't so far away that any liquid water that were there would just freeze onto the surface. It would be in that special Goldilocks zone, not too hot, not too cold, but just right for liquid water to pool on the surface, for ice to be at, say, ice caps if they're there, for vapor in the atmospheres. So TESS will find all kinds of planets, and some of them we're hoping will be in the habitable zone.
All right, wonderful. Well, now it's time to get your questions answered. And if you remember any questions that you had before, let us know using the hashtag AskNASA. Or if you're just tuning in, this is NASA Science Live, where we're talking about interstellar space. So I'd like to invite back Dr. Aki and Dr. Nicole, who joined us earlier. We have our NASA scientists here to answer your questions. So, now I'm getting pinged here. Shaw from Facebook is asking, which exoplanets have water?
Ooh, great question. I can start. So we know of thousands of exoplanets so far, some from TESS, some from Kepler, some from other surveys. And how many have water is a great question. We're just starting to probe that using telescopes like the Hubble Space Telescope, actually. And the James Webb Space Telescope, which should launch in a few years, that will also look for water in planets. So we're just kind of starting the search, but we've identified water in a lot of Jupiter-sized planets so far. And yeah, so I would say maybe tens right now, but they're all Jupiters, nothing quite the size of Earth yet. Anything to add, girls?
No. That was it. I was going to just say, we don't really know, but but her answer was better.
But you could also say we know of thousands of planetary systems, but not all of them are really the ones that are the right ones to take to Hubble to look for the water. So those are a much smaller subset, and those are larger planets too. So as our telescopes get better, we're going to be digging down closer to Earth-sized planets and hoping that those smaller planets will also give us some signals of water.
All right, we're also getting another question from Twitter asking, where is TESS right now?
Oh, okay, that's a great question. So our orbit is really very elliptical. So we come in close to the Earth and we use the DSN to bring the data down. And we have just completed our 9th observing sector in the southern part of the sky. And we've turned the telescope around to do our 10th observing sector as of the last day or so. So it is on its closer part of its orbit. And it's highly elliptical, but it never gets any further from the Earth than the Moon. So we're still very, very close to the Earth.
And just to clarify, so the way TESS works is it takes like a sliver of the sky, right, at one time, and then it builds like a large profile of what the sky is looking like?
Right. It's going to observe the 85% of the sky when we're done with our 2-year survey in slices that we call observing sectors. And it stares at one slice for 27 days straight without blinking. And then it turns and sends the data down. It actually does that twice in a sector, and then it will turn to the next sector. And when we're done with, say, the first year of our observations, if you were to unfold that, you would see that we had painted these observing sectors on the southern part of the sky.
All right, Andrea from Facebook is asking, what makes Earth habitable, and how can we tell if a planet could even support life?
Aki, I think that's for you.
Okay, well, okay, so again, it's funny, I always want to answer all these questions by starting off, we don't know, and then say about what we do know. Now, okay, so we think about the Earth, and the Earth is unique in the solar system. It's the only planet that has a global biosphere with so much life on it, liquid water and so much life, that life is actually changing the chemistry of the atmosphere, the whole atmosphere. The oxygen in our atmosphere comes from plants, there's methane from bacteria. But what makes Earth habitable? Well, we think, as Patty said, liquid water seems like it's required. But as far as the other things that might be needed, we don't really know.
But we know it would make it uninhabitable.
Yeah, it's more like we know what. It's more like we know how to kill a planet, basically. But but for all the other things that might matter, in a way, we want to learn about that by studying the planets around other stars.
All right, thank you. I'm really excited to see what TESS is going to explore next. And these discoveries are helping us understand our place in the cosmos. So, speaking of exoplanets, I'd like to introduce someone who knows a lot about this subject, and that is Dr. Thomas Zurbuchen. Thomas is the Associate Administrator for Science at NASA. So, Hello, Thomas. And just a basic question, even for my own edification, what does an associate administrator for NASA do?
So, together with an amazing team, we run all these science missions we just talked about, including 100 missions looking at the Earth, the planets, the space between the planets, our sun, and then into the deep universe. So we're both setting strategic direction, but also operating those missions. And all these colleagues you've met are, of course, part of that big team.
It really is sort of amazing the breadth of types of science that NASA really is conducting right now. So
it's really amazing. It's just absolutely stunning.
Yeah, and I'm hoping that we will cover a lot of what that is in this show moving forward.
Yeah, you should.
Yeah, but I know that you have a special guest with you today, so I'm going to let you introduce her.
Yeah, this is Anna Humphrey, who is at T.C. Williams High School. You're a senior there.
Yes.
Remember the Titans, right? A Titan right here. And of course, you're here because of the amazing work you've done outside of the classroom. And you're a researcher. In fact, you won an award, Regeneron Science Talent Search Award. And you did research on exoplanets. And just tell us, what did you find?
Yeah, so I was looking at systems where we'd already found multiple planets, and the idea was, is it possible that we're missing more planets in between the ones we've already found? So what I did was I took an imaginary planet, and I wanted to see if I could squeeze it in between two that we already knew about without disrupting the orbits of the two planets that we'd already found. And that disruption would be caused by gravity. So gravity is the thing that pulls us down to Earth, right? So if you have planets that are next to each other, they pull on each other as well. And so I was trying to make sure that that pull wouldn't be so big that it would cause the planets to get ejected from the system.
So
or
that's
crash
really
into
cool.
each other.
So all these planetary systems you have, if you put another one in some places, they work just fine. In some other places, what happens?
Yeah, so if the planet is too large or if it's too close to the other ones, they'll pull on each other, and it can actually cause planets to get ejected from a system or collide, do really exciting things that we don't want to happen in a solar system.
Something that may have even happened here or in other planetary systems.
Exactly.
Let me ask you a question, and that is, do you remember the first time you figured out something nobody else knew?
Yeah, so I remember when I made my big sort of discovery in this particular research project. I was sitting in my grandmother's house over Christmas break, and I was trying to figure out how can we figure out if there are more planets here, if we're missing any. And I had this idea of creating a map using math, and that epiphany moment came. And
an amazing thing. You will never forget that. I never forgot my first moment. Research is amazing, and I hope you'll be a researcher all your life.
Yes, yeah, I hope so too. That's my goal.
Congrats, Anna.
All right, thank you both for joining us. It really is a special thing. I'm so glad that NASA has all this public data that we're doing, that a special person like you can use it and do further research. So that's really exciting. And I want to thank all of you for joining us today. We loved taking your questions and exploring our cosmic neighborhood together. And I just want to remind you that we chose to do this live so that you could become a part of the show and ask your questions that fuel your understanding of the universe. Please join us next month as we take a look at our home, Earth. And in the
And I'm here on the President's behalf to tell the men and women of the Marshall Space Flight Center and the American people that at the direction of the President of the United States, it is the stated policy of this administration and the United States of America to return American astronauts to the moon within the next 5 years. The President has directed NASA and Administrator Jim Bridenstine to accomplish this goal by any means necessary.
Hello and welcome to NASA Science Live, an opportunity for you to come behind the scenes and to get to know your space agency. I'm your host, Sophia Roberts. This show gives you the opportunity to ask NASA scientists questions and then to get your questions answered. So visit us on Facebook or Twitter and ask us a question using that hashtag AskNASA, or leave a question in that comment box wherever you're watching this. But first, here's some of the latest news from around the galaxy, brought to you by our cosmic news anchor, Scott Bednar. Scott, what have you got for us?
Thanks, Sophia. Happy Earth Day, everybody. I am Scott Bednar, reporting live from the Cosmic News Corner, and have I got some news for you. History was made this month when the first ever image of a black hole and its shadow was unveiled to the world. The photo may seem a bit blurry, and you may be saying to yourself, did I just get catfished by a black hole? But rest assured, you did not. This is a really big deal. We've known for some time that black holes exist, but we've never actually been able to image one. Perfect for scrapbooking. It took 8 radio telescopes from around the world working together as one giant Earth-sized telescope to be able to construct this image. Conversely, the unsanctioned Dictionary of Non-Scientific Terms defines black holes as what you get in black socks. Moving on, new findings are helping scientists understand the history of water on our moon. Put your bathing suits away, we're not talking swimming holes, just little wisps of H2O. NASA's LADEE mission has discovered that water is being released from the moon during meteor showers. Let me break it down for you. A speck of comet debris strikes the moon. It vaporizes on impact and creates a shock wave in the lunar soil. When something larger than a speck strikes the moon, this shock wave can breach the soil's dry upper layer and release water molecules from the hydrated layer below it. For those of us without PhDs in geological lunar impact modeling and analytical physics, there's water on the moon. Have you heard? NASA is sending a helicopter to the red planet. Let me repeat that. A helicopter to Mars. Now, this isn't your everyday run-of-the-mill helicopter. With a body the size of a rolled-up guinea pig and twin rotors almost 2 meters wide, this helicopter just passed its final flight test here on Earth. So the next air this mini chopper chops will be in the thin atmosphere of Mars. Look, we've sent orbiters to Mars, we've sent landers, and we've sent rovers. But think of what would be possible from the air. NASA's really taking science to new heights. Meanwhile, it's Earth Day. Have you thrown away all those plastic straws yet? How about planted a tree? No? Well, I've got just the thing to make you feel better about yourself. NASA invites you to take a picture of your favorite natural earthly feature and post it to social media using the hashtag #PictureEarth. It could be a setting sun or a blooming flower or a pile of dirt. NASA's going to take these pictures and turn them into a collage of legit proportions. But I still encourage you to take care of our Earth every day and maybe go ahead and plant a tree. Well, that's all I've got from the Cosmic News Corner. Hungry for more NASA news? Of course you are. All you have to do is tippity-tap nasa.gov into your phone or your sit-down computer, and a world of science will emerge in front of you. Check it out. You might even learn something. Back to you, Sophia.
Thanks, Scott, and happy Earth Day, Earthlings. Today's episode celebrates what makes our home special and weird. As Scott just mentioned, we've been asking you to send us pictures of your environment using the hashtag #PictureEarth. There are already a ton of submissions, including some from other NASA missions, that show how they hashtag #PictureEarth. So take a look on social media, and there's still a time for you to submit your own picture. So during today's episode, we're going to talk about some of the features that make our home weird, how we study our planet, and where we might see these special features elsewhere in the solar system. So remember to submit your questions throughout the show using that hashtag #AskNASA. But before we go any further, let's take a look at how Earth is unique.
Earth. Home. Of all the planets NASA has explored, none have matched the dynamic complexity of our own. Deserts, tropical forests, icy poles. Massive storms rage over land and oceans. A unique atmosphere protects and insulates us. Liquid water spans its vast surface. And a delicate balance of systems gives way to a kaleidoscope of life. Earth is a very special place. From the vantage point of space, the perspective of sky and sea, and all across the land, we study our planet not only to learn about it, but also to protect it.
Earth is weird. There's an active, moving core, a magnetic field that protects our planet, a delicate atmosphere, and fresh water that moves throughout the land and the air. And then there's the weirdest of all, us. So there's nowhere else in the solar system and beyond where we have found life other than our home planet. So, speaking of life, I am joined by 3 experts who are going to help us dive into these topics. We have with us today Anne-Marie Eldering from NASA's JPL, who is working on the Orbiting Carbon Observatory. We have Jim Garvin, who is Goddard's chief scientist, and we have Alicia Joseph, who works on, or is a research scientist here at Goddard. So Earth is special really in so many ways. So I'm going to start with you, Jim. How did we get water on our Earth?
So our planet was born in a magical mystery tour 4.5 billion years ago when it came together. It formed hot. But as it formed, it was collided with by the leftover remnants of all the stuff that made our solar system. Some of these things were water-rich. Comets. They seeded our planet with initial water. And then, as the Earth cooled down, volcanoes erupted, releasing even more water. This water cycle thus began, and it evolved over time to even affect the rocks we live on today on our continents. We are the water planet.
Ooh. And Alicia, how does our water move through our atmosphere?
Well, the hydrologic or water cycle is a fascinating process which describes how water moves above and below the Earth's surface. Water moves from one reservoir to another. For example, ice, fresh and saline water like oceans, lakes, rivers, and aquifers, and the atmosphere by the physical processes of evaporation, transpiration, condensation, precipitation, and surface runoff. In doing so, water goes through various forms like ice in its solid state, liquid, and vapor in its gaseous state.
Yeah, that is really special how our water is capable of moving. And one of the places is through the atmosphere. So, Jim, can you talk to us a little bit about how our atmosphere has formed?
So our planet's special because it's big enough to retain an atmosphere. So after the Earth formed, started to cool down, the oceans were being accreted, the volcanoes and other things in that part of the Earth history released gases. And they slowly built up over time and were affected by our planet, slowly initially, and then eventually by the activity of life. And that's one of the key ingredients that makes our planet's atmosphere so unique.
Yeah, no, our atmosphere is just perfect for us, right? It's got about 21% carbon or oxygen, and that's what we breathe, a whole lot of nitrogen, and there's many other gases in trace amounts. Just want to tell you quickly about 2. One of those is carbon dioxide. It's like a little blanket. It keeps heat in our atmosphere and makes the temperature what it is today, very comfortable. But carbon dioxide's been going up in concentration, something we got to keep an eye on. Another gas you might know about is ozone. It can be a pollutant, irritate you when it's down low in the atmosphere, but if it's high up in the stratosphere, it protects us from UV radiation. So Jim and I don't freckle too bad because that UV radiation's stopped by the ozone.
Thanks.
So one of the things that I don't personally think about originally when we talk about the Earth, but is super important, is on the inside, and that's our core. So Jim, can you please tell us about our Earth's core?
So our planet is special because we have a kind of sweet inner core, a solid, very inner core, and then an outer liquid core that moves. And by rotating, it generates a geomagnetic field. And that field, which is really critical to life on Earth, is the force field that protects us from all that nasty space radiation that if we were beyond it, we would be experiencing. So our Earth is lucky enough to have such an inner core. We look for such elements, such aspects of planets on other planets like Mars, where Mars Insight will be looking for the Martian core.
Great. Well, now's our chance to take some questions from you. So if you've been sending questions in, please remember to use that hashtag AskNASA. Go to Facebook, go to Twitter, use that hashtag, and leave a comment wherever you're watching if it's a streaming. All right, so let's see what we've got so far for our Ask NASA. All right, Vicky on Facebook is asking, how come Earth is the only planet that has water and oceans?
Well, I will say this. First, some of planets and planet-like objects have oceans, but you don't see them at the surface. So, for example, one of the big moons of Jupiter, called Europa, it's about the size of our moon, probably has a bigger ocean than Earth's under an ice shell. Other worlds hide their oceans. Mars, a lot of the water on Mars is frozen in the rocks and frozen as ice. So it's not exactly that all the planets are, you see what you get. So there's a lot of ocean worlds to go discover.
Excellent. All right, Manish on Twitter is asking, how many advances in space technology have helped us on Earth? Ooh.
I think the answer is a lot. I mean, I know there's insulating materials that were developed for space program that have benefited us in our lives. There's probably others you guys might know.
Geolocation and satellite navigation that we now use to precision go to places that we never would have imagined. Laser detection methods that we can use to figure out distances to things that eventually will be in driverless cars. And also things that sense perturbations in our atmosphere that affect our quality of life. These are all sensory things that we've developed in space.
Yes, and every day at NASA, scientists and engineers are continuing to push the envelope and to do research to get us further and to get more information.
Wonderful. All right, Patrick on Twitter is asking, what planet have we discovered is currently the closest in characteristics to Earth?
Well, it depends on how you look at it. So for me, that world would be Mars. Although it has less atmosphere, it's colder because of its position, it still has a history book written in the rocks that we're exploring now with rovers like Curiosity, soon a helicopter. So it really is kind of our Earth-like brother. However, don't forget Venus. She's hiding her secrets, and we got to get to know our sister much better.
Wonderful. So that is all the time we have for questions right now. Don't worry, we'll be taking more later on in the show, so please keep sending them our way and using that hashtag AskNASA or commenting in the stream wherever you're watching. So now let's talk about how we study Earth and why it's important to better understand the complex processes that work on this planet. Anne-Marie, you've been an expert in Earth's atmosphere. Can you tell us, or start by telling us, how we study Earth?
Yeah, so I mean, humans have been studying Earth ever since we lived on it, looking up in the skies and studying what's around us. But there's only so much you learn that way. And now that we have the ability to go to space and study Earth with satellites, you can see the whole global picture over the oceans, all the lands, and really see how things are connected. And I'm going to tell you just a second a little bit about carbon dioxide. This is a map of a model field of carbon dioxide showing you how dynamic it is, how quickly it moves around. And you also can guess from this that carbon dioxide is emitted by humans. When we burn fossil fuels, we put it up in the atmosphere. And I mentioned it's a blanket capturing heat. So when we put that up in the atmosphere and the amount increases, it keeps us really warm. But carbon dioxide is also is dynamic with other parts of our Earth. The plants in the Earth take up carbon dioxide, remove it from the atmosphere, release it when the leaves fall off. And so there's this big dynamic natural carbon. To understand and pull these pieces apart and see why each year can be a little different in the carbon cycle, we're using satellites to do that. We have one in space now called OCO2. It's been up there since 2014, but this is a cool little scale model. This is a model 1/10 in size. The real thing is about the size of a big refrigerator. This is a payload that's going to go up on the International Space Station called OCO3 to continue our carbon dioxide measurements.
And that's supposed to go up soon, right?
A week from Tuesday, April 30th.
Oh, look out for that, all of you out there. New launch.
Yeah.
All right. So we've talked about a little the carbon area, but there's also the water cycle, which is super important. So can you tell us how we study Earth?
So we use satellites, airborne campaigns, and ground instruments to study water. Water is abundant on Earth. Approximately 71% of the Earth's surface is covered by water. However, less than 3% is fresh water, meaning potable or suitable for drinking. And of this, less than 3%, 2/3, is locked up in ice caps and glaciers. So fresh water is rare. We have satellites like SMAP, which is soil moisture active passive, GRACE, which studies groundwater, and Landsat, whose data can be used to study evapotranspiration. We conduct airborne campaigns like SNOWX and ASO, Airborne Snow Observatory, which collect data on snow water equivalent and snowmelt. And this data is important. It helps improve water management, and it guides policies. For example, more than 1.5 billion people rely on snowmelt for its water supply.
All right, you mentioned that NASA has this airborne snow observatory, and 1.5 billion people is an enormous number of people. So, I mean, that's new news to me. I had no idea we relied so much on snowmelt. And we even have some footage from one of the recent campaigns from the field. So let's take a look at that.
ASO is a partnership between NASA JPL and the California Department of Water Resources. ASO operates in 2 states right now. The first one is how much snow water equivalent is up in the mountains, and the second is how reflective or how shiny that snow is. And so those 2 things tell us, 1, how much water we have for our drinking water, for irrigation. How reflective it is tells us when it's going to melt from the mountains. We have 2 instruments on board that look through the bottom of the plane at the snowpack. The first instrument is a giant laser pointer. It's a scanning LiDAR. The second instrument is an imaging spectrometer, which is a fancy camera. With the airborne platform, we can touch every piece of snow with our LiDAR. Right now, we are delivering information directly to the California Department of Water Resources, and that helps them decide where to put water, when to make releases from dams, and how to allocate those resources more efficiently. It's amazing to be flying on this plane in the mountains. At 20,000 feet, you get an epic view of the watersheds. You get a really great view of the snowpack and how it's distributed. And as a scientist, I really love sitting up there and thinking about how I can understand the snowpack more. I start off in the spring working very long days, making sure that everything is going smoothly, but it's really worth it at the end to be able to give that data to the folks that need it so that we can improve our lives and manage our water resources more efficiently.
All right, I hear that some of you are wondering about our NASA spin-off technologies. So if you are excited about learning about NASA spin-off technologies, you can visit spinoff.nasa.gov to learn more. So back to our video stuff. I had no idea before we started the show that so many people relied on snowmelt as a source of drinking water. And it really is incredible how our Earth systems are just so connected to provide us with these really precious resources. So we've been talking a lot about what makes Earth special, but that doesn't mean that it's only Earth that has some of these amazing resources, like atmospheres or volcanoes and even seas. So yes, Earth is pretty weird, but our scientists here at NASA see some of Earth's distinctive qualities elsewhere in the solar system, and really even beyond. So let's take a look at some of the other bodies in our solar system that share some of these features with our home planet. So viewers, this is where we need your help. This is a photo of an atmosphere on another planetary body. Where do you think it is? Type your answers in wherever you're watching this. So is this atmosphere A, Mercury, B, Pluto, or C, the Moon? Another atmosphere. Is it A, Mercury, B, Pluto, or C, the Moon? And the answer is B, Pluto. So what's the difference between this atmosphere and Earth's atmosphere?
So this is an atmosphere you and I would not breathe very well in. It's made up of different types of gases. It has nitrogen in it, and it has some hydrocarbons. Methane is a good example of one of those. It also disappears and reappears almost completely because it condenses out and then goes back up. So it's a very different kind of atmosphere than we have here at Earth.
All right, let's get on to another question. There are volcanoes on other planets too. So where do you think that this volcano is in our solar system? Is it A, Venus, B, Saturn, or C, Mars? Another volcano. Is it Venus? Is it Saturn? Or is it Mars? And the answer is C, Mars. Yes. All right, so how do the volcanoes on Mars compare to the ones on Earth?
So this volcano is called Olympus Mons. It's the biggest volcano we've discovered in our solar system. Literally 90,000 feet high. It's as big as France, one volcano. 5 million cubic miles of rock. It is many times bigger than the closest analog on Earth is Mauna Loa in Hawaii, and its other cousin big volcano is Mont Mons on Venus. So this is the granddaddy. When this volcano erupted, it produced enough gas to fill the Mediterranean Ocean with water.
Oh. Look at that. All right, so there are other seas on planetary bodies too, but they may not be made out of water. So where do you think that these seas are? Is it A, Saturn's moon Titan, B, Jupiter's moon Europa, or C, Mars' moon Phobos? Is it Titan? Is it Europa? Or is it Phobos? And the answer is A, Saturn's moon Titan. Now, are these seas on Titan similar to the ones on Earth?
They're very different. These seas are made of hydrocarbons, and they freeze from the bottom up. And we're seeing them through the eyes of radar flying on a satellite known as Cassini that maps Saturn and its moons. And that allows us to connect a world bigger than our moon, Titan, to our own planet. This is spectacular connectivity between our planets and other worlds.
Ooh. So, did any of you guys get those at home right? We still want to hear from you, and our scientists are ready to answer some more of your questions using that hashtag AskNASA. So, let me see what has come up through my little iPad here. All right, Zachary on Twitter is asking, how did Earth cool down?
Well,
sounds like another gym question.
So, our planet was big and born hot, but eventually, through processes in which heat flows out by conduction and convection, the planet cooled down. But today, the planet's still pretty warm, and we have tens of thousands of miles of undersea volcanoes, the mid-ocean ridges, that help get rid of that excess heat in our planet. But while that's happening, which helps keep our planet nice, while that's happening, the planet's regulating itself inside. And so that's what makes Earth so spectacular. We have action everywhere.
All right. Susan on Facebook is asking, is there evidence of other planets' cores that used to behave like ours?
Well, we did detect the sign of a relic magnetic field on Mars with the Mars Global Surveyor, and that mission suggested that the early Mars geomagnetic field may have been the same size as Earth's. But then something happened. Mars managed to lose its internal magnetic field. So how do you do that? I haven't lost a magnetic field yet. So we need to understand that. That also has consequences for Mars' atmosphere and even for its ability to sustain life today. So a good analog for Earth. Let's watch Mars.
All right. And then Zachary on Twitter is also asking, how big is the ozone hole and has it changed?
Wow, that's a great question. So the ozone hole, I don't have a number in terms of square miles, but I can tell you it's not as big now as it used to be. So for those older folks in our audience, you remember those aerosol spray cans? Mm-hmm. No more of that. We got rid of the CFCs. We've changed a lot of what we produce, and it's had an effect. We're starting to see the repair of the ozone hole.
All right, Kristen on Facebook is asking, what are some of the things we can do to help nurture our planet?
Well, I have a few ideas. One thing we can all do is just buy less stuff. The less stuff we buy, the less has to be made, so that's good. And I'm a big fan of a bicycle. In Southern California, you can bike a lot of places and not get caught in the rain, so it's one thing I do to reduce my driving.
And along those lines, you look at conservation of our natural resources like water and other things. So.
And plant trees.
Yes.
Yeah,
yes.
That's a great idea.
Sorry.
Yes, Scott already told us to do so.
Scott, I'm listening to Scott.
All right, Alicia, we have another question for you, which is how do satellites track the movement of water?
Well, We use satellites to track the movement of waters in various ways. We have several satellite missions that are currently up. For example, we have SMAP, as I mentioned, which is soil moisture active passive, and we track soil moisture using that. We have the GPM, which is the global precipitation measurement, and we use that to track precipitation, water that falls from the earth, and ice. We have missions like ICESat and upcoming SNOWX and the ASO, which we use to track the ice and snow in our atmosphere and on the surface of the earth.
I'm glad we're doing so much to do that. All right, Beverly on Facebook is asking, how does global warming affect Earth?
Wow, that's a long answer, so I'll give you a couple of ideas, and I'm sure the others have more to share. So one of the first things we want to say is that the temperatures have been increasing. We can see that in the temperature record, the fact that many times we see we're the hottest year on record recently. The ice sheets are another place, and the sea level, we see the sea levels increasing, and that ice sheet area is shrinking a bit. So those are all impacts about these warming temperatures.
I mean, we're seeing the total ice cover of the planet changing profoundly. Things we didn't see exposed are now being exposed. Edges of an impact crater in Greenland have now been exposed. We're finding airplanes from 50, 70 years ago that were buried in ice that are popping up, just showing some of those consequences.
All right. So that is all the time we have for questions today, but don't worry, we'll be answering more of them on social media after the show. So thank you for participating and sending them in, and please just keep sending them in. So we've learned a lot of things about Earth today. We've got liquid water, a protective atmosphere, and an active core. And yes, they exist elsewhere, but on Earth, the combination of features come together in a perfect balance, and it gives us this oasis in space. So scientists, considering that, what, in under 5 words, are your favorite things about Earth?
For me, a snowy day on a mountaintop.
Our spaceship Earth is like an island in space, and I love the islands we see, which are kind of mimicking how our planet is.
And I love the regenerative properties of the Earth. The Earth heals itself.
That's wonderful. What is your favorite thing about Earth? Tell us in the comments, and let's hear from some other NASA scientists about what they have to say.
Earth is my favorite planet.
My favorite part about planet Earth is the ocean.
So my favorite part about Earth is there's life here. We know that there is life here. There's so many aspects of it. I mean, the very fact that we're here.
My favorite part about the Earth is the Arctic.
That feeling before a thunderstorm.
I enjoy the feel of the wind.
When you fly, when you are on an airplane, and you are in between 2 decks of clouds.
There are so many different environments on Earth that we are just now exploring in the past few decades.
It actually floors me that we have such a large area on this planet that is, basically relatively unexplored.
The depths of the ocean.
To see that life flourishing under the water.
I think it's fantastic.
I feel like the best thing about planet Earth is that it's so close to the moon, and the moon is awesome.
That the Earth has a large moon that keeps its climate stable by keeping its poles stable.
Coming back up to where does our atmosphere end?
The feedback between life and our climate.
How far out can microbes live?
I like how sunlight interacts with Earth.
How that influences the sea ice.
I just love the diversity of life on Earth and all of the places that it can thrive. It's pretty amazing.
And my favorite thing is carbs, sugar, butter, chocolate, and bread. Well, happy Earth Day, friends. Thank you so much for joining us. Next month, we're going to take you on a tour of storms across the solar system. So we'll see you all next time. Thank you all also. Bye-bye. Hello and welcome to NASA Science Live, an opportunity for you to come behind the scenes and to get to know your space agency. I'm your host, Sophia Roberts. This show really is all about you being able to interact with NASA scientists and to get your questions answered. So visit us on Facebook or Twitter and ask us a question using that hashtag AskNASA, or leave a comment or question in the comment box wherever you're watching this. So here to share some of the latest updates from around the galaxy is our cosmic news anchor, Scott Bednar. Scott, what have you got for us?
Thanks, Sophia, and hello, everybody. I am your cosmic news anchor, Scott Bednar, and we've got some breaking news just in. Are you good at counting rocks? Well, then you won't want to miss out on this opportunity. Just announced moments ago, NASA is inviting you to help find the perfect spot on asteroid Bennu where the OSIRIS-REx spacecraft will collect a sample. But here's the problem. There's a lot of rocks. So we need your help to count, catalog, and create a curated collection of rocks on the asteroid by July 10th. Why? With your mad counting skills, this data will speed up the process in developing Bennu's hazard map, which will be used to select the final sample site. And then OSIRIS-REx is going to go down to Bennu, sweep up some little samples of asteroid bits, and send them back to Earth. All you have to do is look at pictures of this asteroid and tell us what you see. Too long didn't read? NASA is hiring rock counters for an annual salary of $0. Sign up today. It's time to tighten your Van Allen belts because we're going back to the moon. And guess what, Apollo? Your twin sister Artemis is in town, and she's here to stay. NASA's next mission to the moon with humans has officially been named Artemis, after the Greek goddess of our nearest celestial neighbor. And when we land in 2024, the first woman and next man will step foot where no one has ever been before, the moon's south pole. There'll be something for everyone. Boots on the ground, flag planting contests, rock chiseling competitions. It'll be a regular rom-com. Have you ever been to Mars? No? Well, here's your chance. Sort of. NASA is sending a car-sized rover to the Red Planet next year, and your name gets to be passenger in teeny tiny letters. Submit your alias, and it will be stenciled on a microchip that will travel on the rover as it makes its Martian debut. You'll amass mucho frequent flyer miles and get a boarding pass. You can print it out in full CMKY glory, post it on social, slap it on your locker, tack it on your tack board. The possibilities are limitless. It's absolutely glorious. Well, I'm done. But that was just a taste of space. Hungry for more? There's a full-on brunch buffet at www.nasa.gov. Go feast on some science. Back to you, Sophia.
Thanks, Scott. I've already got my name on it, and all of you guys should too. Nearly 1 million people have already submitted their names, so go send yourself to Mars. All right, let's get on to today's topic. We're going to be talking about storms across the solar system, and we're going to start by talking about how storms form on Earth, and then we'll see the conditions that cause them to happen on other planets in a weather forecast from across the solar system. And finally, we're going to take a look at how NASA studies storms on our own planet. And you guys, we're even going to release a weather balloon live during this episode. So if you want to learn more about NASA's effort to study hurricanes, visit nasa.gov/hurricanes or visit NASA Hurricane or NASA Rain on Facebook and Twitter. So our friends over at NASA Wallops Flight Facility in Virginia help forecasters and first responders with severe storms by releasing these huge balloons every 12 hours. All right, Chelsea, can you hear me? What are you doing over there?
Hey, Sophia. Yes, I can hear you loud and clear. So we're here live at NASA's Wallops Flight Facility, where we're going to take you on a behind-the-scenes look at how weather data gets turned into the easy-to-read forecasts that you get on your phone's weather app. So we're going to be launching a weather balloon today. So as the balloon ascends up into about 100,000 feet in altitude, it's going to be taking measurements. Here to talk to us a little bit more about that today is Adam Thomas. Hey, Adam. So what do we have going on behind us here today?
Well, behind us we have a balloon inflation shelter, and Kyle Pilchard, one of our meteorological technicians, has inflated that balloon, and hopefully we'll be able to release it at the end of the show today.
And so what kind of data is it looking for? What do you have in your hands here?
Well, I have a radio sign which we attach to the balloon, and it has all kinds of meteorological instrumentation here, temperature sensor, humidity, also is GPS track, so we get wind speed and direction from this device as it ascends through the atmosphere.
And so about how often does NASA launch these things?
We do it twice a day here at Wallops, twice a day every day, and in some instances we actually do it more than twice a day. If we have hurricanes, severe weather outbreaks, National Weather Service program will ask for more balloon releases. So sometimes we have up to 4 balloon releases a day, especially for storms such as Maria and Florence just recently, where we had to get more data and more up-to-date data with those extra balloon releases.
Wow, that's so interesting that this happens right here. Well, it sounds like we need to get this radio sonde attached, and we got to get this balloon up ready for flight. But in the meantime, if anybody has any questions for Adam here, be sure to send them to us on social media using hashtag AskNASA, and we'll get them answered a little bit later in the show. So we've got a balloon to set up. So Sophia, back to you.
Thanks, Chelsea. I am so excited about this balloon, and I'm really looking forward to it being released later on in the show. So today I have Dahlia, who is a research scientist at Goddard Space Flight Center. And Dahlia, let's just, come back down to Earth and talk about something we're a little more familiar with. How do storms form here?
That's right. So tropical cyclones is actually the catch-all term, but they're called different things depending on where you live. So, for example, in the Atlantic or Eastern Pacific, we call them hurricanes. In the Western Pacific, we call them typhoons, and in the Indian Ocean, we call them cyclones. Now, you need about 3 different ingredients for a storm to form. You need really warm ocean water, you need to have some pre-existing storms, and then you need really humid air. So what happens when a storm forms is that humid air starts to rise, and as it rises, there's more air that comes in to fill it inside. And so we start to have warm air rising. You get a lot of convection, which causes clouds and precipitation. And that movement inward, upward, and then outward starts the storm moving. But because the Earth rotates on its axis, that actually causes the storm to rotate, like we see the eye wall and eye of a storm. And so because that strong pool of warm water is starting to fuel the storm, just like gas fuels our car. As the storm begins to develop, it starts moving faster and faster with stronger winds and more rainfall. And so what we see from space is we can get a view of how these storms are moving and changing, all depending on where the winds are blowing and how warm the surface of the ocean is.
All right, great. Well, we already have some questions
Sure.
for you. So can you tell us, what is the biggest hurricane we've ever seen?
Well, we've had satellites and before that, instruments on the ground measuring this for a long time. But the most intense storm we ever saw is Typhoon Tip, which occurred in the Philippines, and it was 1,300 miles across. That's humongous. It was not only a Category 5 like we think of here, but it was a super typhoon with sustained winds of over 160 miles per hour.
Oh,
I know.
I know. A follow-up question for that is,
Sure.
how damaging are these storms?
Well, so the damage, a lot of the damage is caused by winds, which is what's happening in the eye wall of the storm. Those winds are whipping around in the middle. The eye is actually very calm. But as you get further out, the winds are important, but the rain and the rain bands around it tend to cause a lot of the flooding that we see, as well as the storm surge that pushes that water onto land when it makes landfall. And so it's important to forecast and understand how these storms move and intensify so we can really understand how they're going to impact people once they hit land.
Whew, that's a lot to digest right there. And then just one very quick question, because we talked about sort of like the width maybe a little bit, but is there anything unusual about like heights or like how high up they are?
Sure. So as these storms this air starts to rise, we're able to see 3-dimensional profiles of storms all the way up to 15 kilometers in height. That's high, way higher than where planes fly. And so, with satellites like the Global Precipitation Measurement Mission, we can actually see 3-dimensionally through the clouds all the way up in the atmosphere how the storm is distributed in terms of its heavy rainfall. And that's really important to provide clues to forecasters to understand where these storms might go and, importantly, how intense they might be.
All right, thanks, Dahlia. And we'll be getting back to you a little bit later.
Great.
You may have heard of Jupiter's Great Red Spot. It's only the largest storm in the solar system, but there are actually a lot of other really unusual storms in our solar system and even beyond that. So NASA's chief scientist, Jim Green, is going to take us on a tour of some of these storms in our cosmic neighborhood. So let's find out. What is happening over at what's happening over on Venus, Jim?
You know what? I can actually tell you something that's happening on Saturn right
All
now
right.
as
Great.
we wait for Jim. So one of the exciting things that we can do with the Cassini spacecraft is we are actually able to see lightning and even hear it on the surface of Saturn.
Whoa.
And so the way that we can do that is we actually see the visible light at night. And the storm, it's called the Great White Spot, sort of like the Great Red Spot, is actually so wide, it's almost as large as Earth, 6,200 miles across. But what's unique about these big gas giants relative to Earth is that on Earth we have warm water heated from the sun that causes and fuels these storms like heat engines. But on these big gas giants, we actually think that the internal heat is fueling these storms themselves. And
Like from their core?
Well, just from the heat from when they were born. And so we're still learning a lot more, and some of NASA's missions, that are flying right now as well as in orbit, are going to tell us more about how these storms form, not just on our planet, but all over the galaxy.
Ooh. All right, here's another question from Facebook. And Krista is asking you, what is it like to work for NASA?
You know, it's one of my favorite questions because we work with amazing scientists and engineers every day. And so one of the really exciting things about working at NASA is we have lots of exciting satellite images and information that brings us to model these phenomena on Earth. So what I do is I actually use satellite data from NASA and our partners to model landslides and other natural disasters on Earth. And these provide important information to emergency responders and other groups that are helping to understand, mitigate, and ultimately recover and build resilience for these types of disasters. And so it's been really exciting, and I think important to note that all of NASA data is free and open to the public, and that provides an important set of information for us to really understand and move forward with contributing to understanding disasters around the world.
I mean, it's really wonderful that this data, which is, created for the public, is available just absolutely publicly. So
That's right. And I think, another really important thing is that we work very closely with our partners.
Mm-hmm.
And so, we work with groups like NOAA, which provides operational forecasting for National Hurricane Center, for example, or the Joint Typhoon Warning Center, or the Air Force, all of whom provide operational forecasts. And so by being able to have information like, this hurricane here, where we can really understand layer by layer through the storms how and why these storms are developing. So I know this is kind of a fun tool, but what it really is showing is the three-dimensional profiles of these storms. So the colors below show rainfall, but at the top we can actually see snow at the top of this hurricane. The first time we've ever been able to do that. So information like this is really important to bring into forecast models and help us to better predict the trajectory, the intensity, and the impacts that these storms might have later on. But we can't do it alone, and our partners are critical in advancing our understanding.
All right, thanks, Dahlia. And it looks like our chief scientist, Jim Green, is now available to give us our weather forecast. So, Jim, what's happening on Venus right now?
Thanks, Sophia. I'm dying to tell everybody about some of the weather in our solar system, and it can be extremes. Let's start with the inner planet, Venus. Now, Venus, beautiful set of clouds. We cannot see the ground because the clouds are so dense, and they're moving rapidly around the planet. In some cases, they're more than 225 miles per hour. These are really rapidly moving around the planet. But what about the surface? Let's go down to the surface. Here we see the global surface of Venus, where the reds are the highs and the blues are the lows. And so you can see huge variations in altitude. But one thing to remember is the temperature on the surface of Venus is nearly the same everywhere on the near side, but also on the far side. So both the night and the day side. And that weather can be extreme. We're looking for lightning. We haven't seen lightning on this planet yet, but the temperatures are enormously hot. More than 800 degrees Fahrenheit, hot enough to melt lead. In addition to that, the pressure is enormous, 90 times our own pressure. Well, let's move further out in the solar system. Let's take a look at the weather on Mars. Mars is this beautiful red planet we hardly see any clouds. We can actually look through the atmosphere of Mars right down to the surface. But what is the surface weather like on Mars? Now, everybody has seen the movies, and in the movies, like The Martian, you see the huge dust storms, the extremes that they thought Mars was like. But it's not like that at all. The dust is really wispy. It's really high in the atmosphere. And here you see a before and after global dust storm occurring on Mars last year. And it lasted for about 3 months. And when that dust settled out and fell onto the ground, it coated many of the surfaces. We now have observed another spectacular phenomena on Mars, and that's these dust devils. These dust devils swirl around atmosphere. These are spectacular atmospheric phenomena that we had to get down onto the surface and really experience before we could believe it. Well, our lander, InSight, actually has a weather capability. It has a weather system that measures the temperature and pressure on the surface of Mars. And that variation in one day can be more than 175 degrees. It's a huge variation, but it's mostly below zero. In fact, the average temperature on Mars is about 85 degrees below zero. So bring your winter coat. It's really cold on Mars. Well, as we go further out in the solar system, let's look at the weather on this planet, Neptune. Neptune, which is in the outer part of our solar system, is what we call an ice giant. It's a fabulously beautiful planet, 10 times the mass of our Earth. And when the Voyager 2 spacecraft flew by Neptune in the late 80s, it saw this beautiful dark spot. But that spot faded away over the years, but just recently a new one has appeared. That one has appeared in the northern hemisphere, and you can see it in the top part of the Hubble observation in 2018. Now, this is a spectacular hurricane. This dark spot has winds that are more than 600 miles per hour, and around it the clouds are moving more than 1,300 miles per hour. Wow, the most brisk winds in the solar system are on Neptune. Well, what is it like here on Earth? Sophia, let's talk about hurricanes on Earth.
All right, thanks, Jim. And I think our friends over at Wallops are ready to release their weather balloon. So, Chelsea, how is it going over there?
Hey, Sophia, and welcome back to NASA's Wallops Flight Facility. So it seems like we've got our radio sonde attached, we've got our balloon fully inflated, and it's just over here, ready for flight. But before that, can you tell us a little bit more about what we're about to witness today?
Well, we've got a beautiful day for a balloon release here at Wallops. We're going to see the balloon release here in just a minute or so. And as it ascends into the atmosphere, we're going to see it go through the troposphere and then eventually into the stratosphere before it reaches about 100,000 feet or so. And that's where we'll see it pop and we'll start to see it come back down. But we're going to get a lot of data from that, so it should be very interesting.
And so other than sending this information to the National Weather Service, what else is this data used for?
Well, here at Wallops, we do a lot of orbital and suborbital launches that require us to do balloon releases during the countdown. That provides a safety group here with a lot of information, a lot of meteorological data is given to them during these releases. So we'll do about one balloon an hour during the countdown, and then as we get closer to T-0, we'll actually go to about every half an hour. So they have a lot of information to determine if we are go or no-go for launch.
Wow, so how many launches does that end up being altogether for a launch?
Generally, we can do as many as 10 or 15. I think with the last resupply mission to the space station, we actually did 15 balloon releases throughout the countdown. So the meteorological technicians are very busy.
Well, hey, speaking of launches, are we about ready for this countdown?
I think so. Let's get to it.
All right, is everybody ready? Let's get going. 5, 4, 3, 2, 1. There it goes. So as this balloon ascends, what does the data look like as it comes back to you?
Well, the first data that we get back in the weather office is in the form of what we call a skew-T diagram, which provides us with a lot of temperature and dew point information up through the profile, also wind speed and wind direction. And we look at that diagram to get basically an overall assessment of the atmosphere. So if it's a stable atmosphere like today, or sometimes we have an unstable atmosphere where we can have thunderstorm activity, that's a very important part of our diagnostics that we do for weather forecasting.
Well, it seems like we're almost ready to take NASA social questions, but before that, I have a quick question for you. So it seems like this is a ton of data that we're getting back, but does this paint the full picture for weather?
Not entirely. We do have this radio sign information going into the computer models, but this is all sent to the National Center for Environmental Prediction with NOAA. In addition to that, we have NASA satellites. We also have NOAA satellites with their GOES and POES satellites. We also have surface observations, radar data that are all included with that data set. So it's a big collaboration of data, but the balloon is really our highest resolution data that we get. It gives us data back here at Wallops every second as it's ascending into the atmosphere.
Wow, thank you for answering all of the questions that I had. But I think it's about time that we take some audience questions here. I wanted to remind everybody that if anyone has any questions for Adam, to send them over to us on social media using hashtag AskNASA. Let's take a look at what we have here. So it looks like our first question is from Twitter, and who wants to know how big is the balloon?
Well, as you can see, when we just released it, it's about 6 feet in diameter. But the interesting part is when it goes up into the atmosphere, the pressure drops. So the balloon actually expands as it goes up in height. So on a successful launch, if we get it up to about 100,000 feet, the balloon will expand to about 20 to 25 feet in diameter, or as big as a small building in some cases before it pops. So it gets very large as it ascends in the atmosphere.
Oh, wow, that's really cool. So we've got another one here from Facebook, from a Facebook user, Katie, who wants to know, do balloons take off in other places?
Yes, actually, we're one of about 92 sites in the United States that have a balloon program with the National Weather Service. So we do 2 balloon releases a day, but here at Wallops, but in other sites, they also do 2 a day to really have a full scope of data coming from the entire country. And throughout the world, we have many, many balloon releases as well. So it's very important data that gets fed into our computer models that we as forecasters use every day.
Okay, we've got some good ones coming in here from Twitter. How much mass can a balloon carry?
Well, it doesn't need to carry much. That radio sound's very light. So as it goes into the atmosphere, it ascends and brings that instrument into the atmosphere, into the stratosphere, actually, to about 100,000 feet. So it really doesn't have much weight hanging from the balloon.
Very cool. So we've got another one here that asks, can we see weather balloons from space or from airplanes?
You can see them from airplanes, but one thing that we definitely want to make sure of when we do release these balloons is to get clearance to release the balloons. We don't want airplanes flying by as we release those balloons. We do not want them going in through the engines of these airplanes. So definitely want those cleared out of the way. You can see them from an airplane, but they know when we're releasing balloons that they don't run into one of them as they're ascending into the atmosphere.
So it's not very likely that we'll ever see one looking out the windows of our airplane?
Not very likely. Not very likely. If so, it'll be at a distance.
So another person wanted to know how high does the balloon travel and where does it collect the data?
So about 100,000 feet is generally where we are satisfied with the balloon. We have gotten balloons as high as 115, 120,000 feet. The requirement is about the 400 millibar level. If you go below that and you have a failure, then we have to do another balloon. So that's the level that they needed to get to in order to be successful.
That's really cool. Well, thank you, Adam, for joining us and answering all the questions that we had online. I think that's just about all the time that we had. We hope you enjoyed seeing our balloon. We're going to be doing it again this evening, right?
That's right. Yep. Every night.
All right. Well, thank you so much for joining us here at Wallops. Back to you, Sophia.
Thank you so much, Chelsea. It was really cool to see the balloon being released. But we're also here back with Dahlia. So just go back to some Earth storm stuff. So can you tell us how we study storms with NASA?
Sure. So NASA and our partners, we have a lot of different assets that are allowing us to look at storms both in the tropics and up to the poles. We have satellites like the NOAA-NASA GOES satellites. That's at 22,000 miles up and take a view of the Earth all at the same time, being able to look at the top of the clouds and the temperature. Further down, we can start to look at how the storms are distributed. We talked about GPM a little earlier in the show, but we have other satellites like the Cygnus constellation, which is super cool. So we can look at global precipitation using GPM and other products that tells us about not only rain in the tropics, but all the way up to the poles. And satellites like Cygnus have a constellation that actually uses GPS signals bouncing off the surface of the ocean to tell us about wind speeds in these storms.
Wow.
Yeah.
And I'd also mentioned earlier, but these data is helping first responders. So can you also talk a little bit about that?
That's right. So being able to understand the impacts of these storms, the first and most important thing is about forecasting them, right? So NASA provides research, and with our partners at NOAA and other centers, we can provide accurate forecasts, or they can provide forecasts of where storms are going. But there's other satellites up there and airborne information that can provide us about how these storms may impact people. For example, we can look at how vegetation changes as a storm passes over. So this is an example of, we can see before and after Hurricane Maria moved over Barbuda. And you can see literally that and the Virgin Islands, that all of the leaves on the trees in these areas were completely blown off. And that affects ecosystems, and it affects the recovery of an area. Another example of how we can understand impacts is looking at rainfall accumulation. So we talked about how the rain bands in these storms can cause a vast amount of rainfall. Hurricane Harvey, for example, caused over 40 inches of rain to fall over the Houston, over the Texas area. And that inland flooding is critical for groups to understand, like FEMA, to provide information and help when these storms pass. And also, we can look at how humans are impacted, looking at things like power outages. So from the SUMI NPP mission, this is an example of Puerto Rico after Hurricane Maria went over the island. And you can just see how the power has changed in terms of loss of power, and then we can look at satellites to see how power has been restored across the island. Really important signatures for how we can help in the recovery effort.
Yeah, that's really great that we were able to provide that information to those really useful things. So what other storms, I'm getting here, does NASA study other than hurricanes?
So as we said, hurricanes and tropical cyclones really occur in the tropics to mid-latitudes. But we also have satellites that can go all the way up to the poles or the Arctic and Antarctic Circle to look at how these storms change from tropical